Oh, we didn't. Those are a lot of information.
Oh, you missed You missed those.
Okay, you can have your calculators out.
Oh, I got
So today we're talking about graphing cosecant and secant graphs. The good thing is that if we know what a sine and cosine graph looks like, and on the quiz we learned how to adapt to a new period. Adapt to a new a new period, finding a new a value, amplitude, shifting it left and right. So the good thing is that everything that we do with sine and cosine, we can just basically do that for cosecant and secant. And just understand that if we can graph the sine and cosine, the cosecant and secant are just built basically on top of the sine and cosine. Now the sine and cosine is not part of the secant and cosecant graph, but they are nice boundaries, and they provide the shape for your cosecant and secant graph. So if we treat cosecant and secant like a sine and cosine, if we can sketch the sine and cosine, then the cosecant and secant are easy. You can just kind of build them on top of these asymptotes and these dotted lines that we're going to create with sine and cosine. So, but let's start off with understanding that cosecant is the reciprocal of sine. So cosecant, which is CSE, you know that cosecant of theta is simply just 1 over sine of theta, right? So to make it a little bit easier, these are all the values associated, y values associated with sine. Now, we only did the easy points to graph, right? We didn't do all the 0.707 to 0.866. We just did the quadrant order pairs like 0, 1, 0, -1, 0, right? That's what we associate with sine, and that's fine. We're just going to look at the detail in terms of the reciprocal. And then once we get that picture out of the way, then we'll have a much more efficient way of getting it. But at least right now, I just want us to be convinced that cosecant is the reciprocal of sine. So what we're going to do is we're going to take all these y values that's nicely provided, and we're just going to do the reciprocal of it. We're going to do 1 divided by this number. 1 divided by sine will give us the cosecant y value at that point. So one at a time, we're just going to insert into the calculator, and we're just going to go to 2 decimal places. Okay, so if our sine value is 0, then cosecant will be 1 over 0. What do you know about 1 over 0? It's undefined, right? If you plug in the calculator, it'll complain. So we know it's undefined. Yes.
I lost my calculator. Do you have any like?
Yeah, you can grab one from that bottom shelf there. Okay, next up, we know the sine value at pi over 6 is 0.5. So then we do the reciprocal of that, 1 over 0.5. And what did that give us? Again, what's 1 divided by 0.5? 2. Okay. Okay, next up, we know the y value for sine is √2 over 2, which is 0.707. And what is 1 divided by 0.707? 0.41. Right. Okay, so we're just going to go down the line here. Keep doing it. Keep going in your calculator, and I'm just going to start filling this in. Okay, let me know how those values look and whether you're getting those as well as you are using your calculator. Any questions? Okay. All right. We're gonna graph those points a little bit, but we're gonna take a break from the from all these order pairs, and I just want to think in terms of sine. Okay. Now we know what a sine graph looks like. We know that we can graph the sine easily if we just look at those nice order pairs. So we're just gonna, if you can just fill in the quadrant order, the quadrant x value. So there's pi over 2, pi, 3 pi over 2, and 2 pi. And I'm going to go a little further here. I'm going to go past 2 pi here. So this is 4 over 2. So this is 5 pi over 2, 6 pi over 2, 7 pi over 2. It's going to go all the way up to 4 pi. And the reason is we want to kind of see 2 periods worth of sine, and then we can kind of see how the cosecant, see kind of a fuller picture of the cosecant graph. But I want us to graph the sine graph in a very faint, either dotted line or in a faint color, because the sine graph is not really part of the cosecant graph, but it does provide nice boundaries for us to build the cosecant graph. It makes it a lot easier to graph the cosecant graph, basically. So, all right, what do you know about a sine graph? Starts where? 0, then it rises up to what? 1, right? Right, and then back down to 0, then -1, and then back up to 0, right? So we know that's a full period for a sine graph that has not been that where the period has not been changed. Let's just create another period for another cycle for the sine graph. So imagine this is 0. We're going to go up 1 again, down 1, or sorry, to 0, -1, and back up to 0. Okay. Now, again, this is not part of the cosecant graph, but it does provide very good, easy boundaries for us to work with. So if we can just use dotted lines, because we don't want to mistake this for the cosecant graph. This is not part of the graph, but it is very helpful. It's just nice to see the sine graph in the background as we're building our cosecant graph. Okay, so we're really comfortable with this, right? We're comfortable with sine graph. We've been working with it this past week, and we just demonstrated our knowledge of it on the quiz. Okay, good. Now, wherever the sine graph touches the midline, in this case, the midline is 0, or our d value. Okay, so I'm going to just put a note here. Our 0, this is our quote unquote center of the graph. This is also our d value. Also, we call this the midline. So right now, there's no shift, right? But it's the midline, it's the center. Now, wherever the quote unquote sine graph crosses, or this imaginary sine graph crosses the x-axis, that's where your asymptote for your cosecant is going to occur. And it kind of gives us more additional boundaries. So I want us to create dotted line, vertical asymptote, wherever you see those intersections with 0. So we see an intersection with 0 at 0. So go ahead and put a dotted line here. Okay. Where else do you see intersection with 0? Yep. So make a dotted line here. Vertical asymptote. 2 pi as well. 3 pi, and 4 pi. Again, none of this is part of the cosecant graph. Okay, so that's why we're putting everything in dotted form, because I see sometimes students on the test, they would make all these solid lines, including the sine graph, and that's incorrect, right? Because we have to understand this is all not part of the graph, but it just helps us with our graphing of cosecant. Everybody good so far? We just have a sine graph, and then wherever the graph crosses the midline or the d value, we know those are the asymptotes for our cosecant graph. Now, let's try our best to plot these points, and we're going to see that a certain shape is going to occur. So at pi over 6, which is the first tick mark there, we're going to go all the way up to 2. At pi over 4, which is the next tick mark, our cosecant y value is 1.41, so it's a little bit lower. Pi over 3, the next tick mark over, 1.15, so a little bit above 1. At pi over 2, it'll be 1. It's the same as that max, that peak of our sine graph. And then keep going, 2 pi over 3, 1.15. Next up, 1.41. 5 pi over 6 is at 2. Now we're going to connect those dots. What shape does that look like to you? Right? Parabola, yep. And so that's basically what your cosecant graph is going to be looking like. It's going to look like a series of parabolas that looks like it's bouncing off of these imaginary sine graphs. And the asymptotes kind of gives us an idea of how wide to make these U-shaped graphs. So that's basically one portion of your cosecant graph. Okay. Now let's finish out this cycle here. So from pi onward, we're going to go to 7 pi over 6. The tick mark after pi is 7 pi over 6. We're going to go all the way down to -2. Negative 1.41. Negative 1.15. Negative 1.15. Negative 1.41. Negative 2. And so if we connect those dots, what does that look like as well? Parabola-shaped graph, but now it's opening down. Yep. So that's it. That is your cosecant graph. Again, the dotted line is not part of the graph, but we include it on our graph to kind of help us with the boundaries, right? We know how high those parabolas are going to go. We know those asymptotes. We know how wide to make those parabolas. So this completes one cycle, because after 2 pi, it'll begin looking like this again. So we can fill this out without having to look at ordered pairs, right? We kind of just sketch our graph out. So we know that. So basically, if you can create the sine graph and these asymptotes, just think of it in terms of, oh, I'm just going to have these parabolas bounce off of the peaks and valleys of my sine graph. And that's basically my cosecant graph. So I see a peak for my sine graph. I'm going to basically create a reflected version of that dotted line sitting above my peak. So the maximum for my sine will kind of correspond with the minimum of my cosecant. And the same thing here. We're just going to make a reflected version off of that valley. So your cosecant graph is just that. It's just a series of up, right side up U's and upside down U's. Technically, these dotted lines are not part of the graph, but we put them there to help us form the graph a little bit easier. That makes sense. Okay. So likewise, the secant graph is the same thing, right? If we can create the cosine graph, we'll create the cosine graph, we'll drop all these vertical asymptotes wherever the cosine graph hits the d value, and same thing. But you can just imagine that your cosecant graph will just look like it's a shifted version of cosecant, because the peaks and valleys for my secant will just be a little bit off. Okay. So hopefully you guys feel like this is an easy process, right? Because if you can do sine and cosine, then you can kind of just use those sine and cosine as dotted lines, and then just put the cosecant and secant off the peaks and valleys of your sine and cosine. Okay, let's continue with the bottom half here. The period. So period of your cosecant and will match the period of your sine. So whatever, a lot of information that you gather from your sine will carry over to your cosecant. So that's why we like to always just think in terms of sine and think of cosecant as just, you know, just an additional step to get that picture. So period of cosecant, just like sine, for the parent graph will be what? 2 pi, yep. And if there is a stretch or a compression with cosecant, we just have to adapt. We just have to find that stretch and compression for sine, and whatever we find for sine is also going to correspond with cosecant. Okay, why is it not pi? Okay, so the reason why, why do you think that is? Why is the cycle not complete with just this portion? Why does it take this and this to complete the cycle? Right, because it doesn't repeat itself until after it finishes both the right side up and upside down. So even though they're both U-shaped, it doesn't create that cycle again until after 2 pi. So it's not going to show up, that right side up is not going to show up until after 2 pi. And likewise, we see 2 periods, right? It takes the right side up and upside down to create a full cycle. Okay, all right, good. Domain. Your domain for cosecant is, well, we look at the asymptotes, right? It exists everywhere except where these vertical lines are. Those vertical lines are kind of breaking up all these cosecant branches of the graph. So we say all real numbers. That's what this two vertical lines with an uppercase R indicates, that it's all real numbers except these vertical asymptotes. And these vertical asymptotes are all at these nice incremental values of pi. So we say except at pi times n, and that n could be a whole number. It could be -1 pi or -2 pi or 3 pi or 4 pi or 6 pi, basically all the whole number integers. We just have to indicate that, okay, we don't want n to be just anything. We have to let n be an integer. It can't be like 0.1 or 0.6. So we say n is an element of an integer. So just you can create a 7 upside down 7 with it looks like a z, and that just means that, oh, as long as n is an integer like a 0 or 1 or 2 or -2 or -3, this will, you know, we're basically able to list all the possibilities of all these asymptotes showing up. Yes. Good. Okay, so the z is a notation for integer. So that's the integer notation. An integer is like numbers like -4, -3, -2, -1, 0, 1, 2, 3. Yeah. Yeah, so that's just a funny looking notation that represents an integer. And this just means that, oh, I just want to restrict n to be integers. I don't want n to be like an imaginary number or a decimal or irrational number. As long as I can restrict it to an integer, pi n will give me all the places where asymptotes will occur on this graph, on either ends of infinity.
You can explain that.
Right, oh, this part right here?
Yeah.
So basically, this is saying that I want n to be an integer. And that's what this notation is. I'm forcing n to be an element. So it says that this is n is an element of an integer. So, and I'm restricting n to be just within the family of integers, and that's what that e is. It's just an element of. Okay, does that make sense? Okay, now range. Let's look at the range here. Range is the set of y values that the graph occurs. So let's look at. We'll start at the lowest y value that we see. What's the lowest y value that we see for our graph? Good. So it goes from negative infinity, right? That arrow tells us negative infinity. So negative infinity. So let's follow the graph all the way up. Now, how far up does the graph go? -1, but then there's a break, right? So we say negative infinity to -1. Okay, do we put a bracket or parentheses there? Bracket, because actually does touch that point. So bracket, and then comma, we're going to skip this space, right? Because our cosecant graph is not going to live in this space. We have those dotted lines, but those dotted lines are not part of the graph. So we're going to skip all the way up to where do we pick up again? 1, and then from 1 to, yeah. So let me know if that makes sense. Yes.
Like a union.
Yes, you can do comma or you can do a union. Union just means that I'm skipping an interval and picking up elsewhere. So if you want to do a union here, you can. Or you can use a comma. Either way is fine. Yeah.
For domain, are we gonna have to memorize it?
Yes, that's right. For domain, we'll have to. Now you can kind of look at this and say, oh, these are all nice integers here. So I can just do n pi. Because it keeps going, right? These asymptotes will, and we don't want to list all of them, so we just want to create a rule that will get to all of them if we needed to. Okay, so graph the cosecant function, plot your points like you're graphing a sine. You'll have vertical asymptotes wherever you see points on the. Right now it's the x-axis, but we really want to think of it as the d value. Or the center. Or the midline. Because it's not always going to be the x-axis, because if the graph shifts up and down, then we have to shift everything with it. So the better answer is the d value. Whatever the d value is, that's the center of your graph, and that's where your asymptotes are going to start showing up. Okay, so you're going to plot these parabolas at the max and min points. Okay, so that's what we did, right? All the max and min points is going to be where our parabolas are going to kind of reflect off of. So your max points, your parabola is going to open up, right? All the peaks of your sine graph is where your parabola is going to open up, and all your valleys, your minimums of your sine graph is going to be where your parabola is going to open down, or your and then your min points, your parabola is going to open down. Now let's look at the secant graph, because secant graph is very similar. We're just going to build off of the cosine. So let's go to page 17. Any questions with this page? So now let's do the same for cosine and secant. Graph the cosine in one color, then graph secant in another color. So, but I'm just going to do cosine with dotted lines. because I know it's in the background. It's not going to be my true secant graph. It's just an imaginary cosine that's going to help us help shape our secant graph. All right, so I'm going to go ahead and put pi over 2. I'm going to create 2 periods of cosine. Okay, so let's do cosine graph from memory here. Where's the cosine start? 1, then it goes to 0, then 1, 0, and back to the peak. All right, cosine has a cup-shaped graph, so we just keep going. We're going to go to 2 periods worth here. We're not going to worry about plotting all those decimal points because we already have an idea that how our parabola, our secant graph is going to look. So use dotted lines to create your your imaginary cosine graph, because it really is in the background. It's not what we're really after, but it just makes the secant graph a lot easier to plot if we can kind of have this in the background. Okay, where are we going to drop our vertical asymptotes? Yeah, starting at pi over 2, right? Wherever this midline is, the center of our graph. In this case, it is the x-axis, but it's not always going to be the case. So the cosine graph, oh, sorry, the secant graph is going to look a little bit off, because if we're starting here, it's kind of cutting things off a little bit. So how much of the parabola is going to show up if I'm forcing the graph to start here? Only half of it, right? Because the other half is not showing up. I mean, I could, but I'm just going to force my graph to start at 0. So I'm only going to have this portion show up. Does that make sense? I mean, I can draw the other parabola here, but it's I'll have to kind of shift the graph over to the left a bit, but I'm forcing my graph to start at 0. So what's going to happen here? Parabola that opens down, yeah. So I'm just going to find the peak and valley and just create kind of a reflected version of it, and that's my cosine graph. Or sorry, my secant graph. Now here's a full parabola, right? But where does the cycle end? Cycle ends here, right? So, I mean, we still have 2 parabolas, but it's kind of like we see one half of one and one half the other. But do you guys agree that this is a full cycle? Because after this point, then my graph is going to look the same, right? Now we can avoid this if we shifted the graph, if we started our period at negative pi over 2, and then we can get 2 full graphs, but it's just because we're looking at from 0 to 2 pi. So it looks like it's getting cut off. Both the upper parabolas are getting cut off. But I want to convince you that that is one cycle. And then if I were to repeat the process, I would be able to create a second period. So I'll use different color here, right? The red and blue are going to repeat. Yes, yeah. So my period is still 2 pi, right? Just like cosine. So I forgot to add those categories below. So with that little space that you see above number one, if you guys can write this out, period. Domain. Now our domain is, okay, it's gonna look even uglier than the previous one because notice that it's not at increments of pi, it's increments of pi over 2, but then starting at pi over 2, we're gonna keep adding pi and that will take us to the next asymptote. So we say our domain is all real numbers except these asymptotes, and these asymptotes are starting at pi over 2 plus n pi. So if I start at pi over 2 and if I keep adding and subtracting n pi, I'm going to be able to reach the next asymptote. And it's just like before, we want to restrict n to just be to be just integer. So we say n is an element of an integer. Okay. What do you think the range is for my secant graph? Good, same as cosecant, right? Go from negative infinity to -1. Skip an interval, you can do union or comma, and then pick up at 1 and 1 to infinity. Again, you can use union, you can use a comma, but basically we need to skip an interval. That union just says, okay, I gotta skip an interval and pick up again because I have a break, I guess. Right, domain. So basically, domain is basically where the graph exists from the if I'm looking from left to right. So you can tell that the graph exists everywhere except these dotted lines, right? So basically, I'm listing out all the places where all these vertical lines are appearing. That's right, those borders. So I'm listing out where all those borders are, and those borders are all occurring at these increments of pi. I mean, starting at pi over 2, but then plus n pi would be, if I add another pi, I can reach my other break. And then if I keep adding another pi, that's where my break occurs. So that n pi just allows me to reach all these vertical lines that are breaking up the graph. Any questions there? Okay, so let's look at number 1. And we're really just going to pretend like we were doing these problems from a quiz perspective. Okay, we're just going to graph the sine. And just like how I did with the table and with the a value and with the rewriting, everything from a science perspective. And at the very end, once we have our sine graph kind of put on paper using dotted lines, we can save the easiest part for last, and that is just creating all these parabolas that are the true graph. But we're just going to treat this. So whenever you see cosecant and secant, just pretend like you're doing sine and cosine and treat it like how you did on the quiz. And at the very, very end, then we can kind of quote unquote convert to the true graph that we really want. So again, sorry, not providing you enough space. So feel free to grab scratch sheets, or if you have space on other pieces of paper. We're going to do number 1 and try to find room for number 2. Hello.
So that's the question. Yeah. Yes, yes.
So we see cosecant. We see cosecant, but we're going to just pretend like we're doing a sine graph. Okay, so I know that ultimately we're doing cosecant, but we're just going to pretend like we're doing the sine graph and treat this like you would on the quiz that you just took. Okay, so first things first, we're going to rewrite it to get that b value to be a better place. Yeah, so I'm going to make it as familiar as possible. So I'm just going to pretend like I'm doing a sine graph, and at the very end, I can adjust it to the cosecant. Okay. Okay, what can we pull as the b value here? 1/4, yeah. Because we know that this is not in the correct form, right? Our phase shift is not showing the true phase shift. Okay, we need to make an adjustment, right? A 1/4 is coming out, so what adjustment do I have to make with this pi over 8? What do I need? Yeah, 4 needs to live in numerator, right? Because I gotta balance that out. A 4 is out, 4 in the denominator is out. I need to balance it up with a 4 up top. Okay, do some cleanup. Okay, what is 4 pi over 8 reduced to be? Pi over 2. All right, so everything now from a science perspective, we know our a value, we know our b value, we know our c value, we know our d value. Period formula. Okay, build our interval. Okay, create our table. Starting at 0, we can keep adding 2 pi. Okay, account for our phase shift. Which direction are we moving in here? Left. Four over two minus 1/2 is 3/2. 8/2 minus 1/2. 12/2 minus 1/2. 16/2 minus 1/2. Sine starts at 0. Multiply by your A value. Okay. Add another column to deal with the D value here. We're going to subtract 2. So take all the most up-to-date Y value and subtract 2 to make all your important points shift down 2 units. 0 minus 2 is -2. -3 minus 2 is -5. Okay, so we look at the top row and bottom row, because those are the Y values that it's going to be useful to help us create the sine graph that we ultimately want. Remember, your D value is -2, so you know that everything is going to get, that's your true center right there. Understand that that dotted line is now your true center. Okay, you're going to just go through the process, graph your sine graph. -π/2, we're starting at -2. 3π/2, we're going down to -5. 7π/2, back to -2. 11π/2, up to 1. 3π/2, back down to -2. And again, all of the work is from the science perspective, but we also understand this is not the true graph that we really want to graph. So you're going to put dotted line because it's really in the background, right? You want your sine graph in the background. It's not the true graph that we're after. But it's very helpful, right? It's going to makes graphing the cosecant a lot easier. Now, where do we want to drop these vertical asymptotes? Yeah, these asymptotes will be dropped wherever the sine intersects with the what? Good. -2, not with the 0, right? With your D value. So basically where your dotted lines are intersecting, that's where we're going to create your vertical asymptote. So you have all these dotted lines here, and all these dotted lines are just kind of creating these background information for the true graph that we're going to need at the very end. Okay, my graph is not to scale and it's a little bit ugly here, but so we've done all the background information. What is our final graph going to look like? Just these parabolas, right? Where we're going to put these parabolas. The first one is going to open down, right? It's just off the valley. It's just going to be a reflected version. Sorry, it's not very pretty, but it's meant for it to be more centered. And then where's the other one? Bounces off of the peak, right? That's a full cycle. Okay, again, all these dotted lines are not part of the graph. The only thing that's part of the graph are these solid blue lines that I have. But we want all those dotted lines to kind of help us so that it's easy for us to do our final graph. Okay. All right, we'll pick up tomorrow. Go ahead and grab your phones.
Okay. So these vertical asymptotes always touch where the D is.
Where the
Not
D is.
zero.
Not 0.
Happen to be 0.
It happens to be 0. Okay.
Bring it up.
Yeah.